All right, guys, welcome to our lesson on what are called reaction mechanisms, remember, which is in our kinetics unit, which has to do with the speed of reactions. It says, wait, you're breaking up. Wait, you're breaking up? Power punctuation. Collision model. In a chemical reaction, bonds are broken, new bonds are formed. That's what's happening in a chemical reaction. And in order to do that, molecules can only react if they collide with each other, right? So they have to have sufficient energy in order to break the existing bonds. So not only that, molecules must collide with not only enough energy, they also have to have the correct orientation. So look at two molecules here. For example, let's say they have to collide with these facing each other. And so then you can see the products obviously are different than the initial reactants, indicating there was an effective collision. Let's kind of see how that would look.
For simple reactions, for example those between atoms, the frequency factor A in the Arrhenius equation can be equated with the frequency of collisions between reacting species. However, for more complex reactions, the orientation...
Let's see an incorrect
this reaction is
orientation.
most favorable when the potassium atom collides head-on with the iodine atom in CH3I.
Here's a
In this
potassium ion.
reaction simulation, the potassium atom collided with one of the hydrogen atoms of CH3I. With this collision orientation, few or no products are formed.
So, guys, in that situation, there was a collision, but the correct atoms didn't come in direct contact with each other, and so that resulted in an ineffective collision. So no reaction. But now look,
This reaction
this
is
is
most
turned around
favorable
now.
when the potassium atom collides head-on with the iodine atom in CH3I. Otherwise, few or no products are formed.
So in that case, there was the correct orientation, and then we had an effective collision. Okay, it says there is a minimum amount of energy required for a reaction, right? There's a minimum amount of energy necessary to overcome the initial bonds. That's called the activation energy, and we abbreviate that E sub A. E for energy, and then sub A for, it's kind of like when she's putting, right? If she doesn't hit the ball with enough force, it'll come back down the hill, but if she hits it with enough force, there'll be enough energy for the ball to go over the hump, and that would indicate, so the hump in this case is representing activation energy. Okay, let's see an example of that.
When molecules collide, there must be a minimum collision energy for the reaction to occur. Lacking this energy, the molecules remain intact and no change results from the collision. This is an energy profile for nitrogen dioxide, NO2, reacting with carbon monoxide, CO, producing nitrogen monoxide, NO, and carbon dioxide, CO2. Click on each of the regions, A, B, C, or D, as they appear to view the molecular changes that occur during each stage of this reaction.
So recognize this is an exothermic reaction because we see the products here are lower in energy than the initial reactants we started with.
As the two molecules approach each other, an attractive force begins to form between one of the oxygens of nitrogen dioxide and the carbon of carbon monoxide, which is indicated by the dashed line. The bond between the nitrogen and oxygen of NO2 begins to weaken, and the bond length increases.
Okay, so you can see there's an increase in energy at this point as these two reactants are coming in contact with each other.
When molecules collide, they form an activated complex, which is a temporary species formed by the reactant molecules as a result of the collision before they form a product. In this reaction between nitrogen dioxide and carbon monoxide, the activated complex is NO2CO. The activation energy, which is the minimum energy needed to initiate this reaction, is 132 kilojoules per mole.
So you guys see this is to be called the activated complex. So in the reaction, this has to form in order for the reaction to occur. But you'll notice that this is neither a reactant or a product, it's just an intermediate. And then you can see it's at its highest energy state. And therefore, the energy necessary to produce this activated complex, that is the activation energy. So it requires 132 kilojoules for every mole of our reactant species in order to produce NO2CO, okay? But you can imagine at a high energy state, this is a very unstable complex, and so it's only going to last momentarily.
At this point in the reaction, the bond between carbon and oxygen continues to strengthen, and the bond between nitrogen and oxygen continues to weaken.
Okay, so now you guys, new bonds are forming, whereas this bond, right, it required energy to break the old bonds. Now, new bonds are forming, and that results in the release of energy. So you guys see, this is the exothermic portion. This would be the endothermic, in which energy is absorbed in order to reach the activation, the activation energy to produce the activated complex. And then as new bonds are forming, energy is being released.
A bond is now formed between carbon and oxygen. The bond between nitrogen and oxygen has broken. The products of this reaction are nitrogen monoxide and carbon dioxide. The products are more stable than the reactants. The products have a lower potential energy. In this type of reaction, heat will be released by the reaction to the surroundings. The heat released by the reaction is 226 kilojoules per mole. This is an exothermic reaction.
Okay, and you guys can see overall it is an exothermic reaction because more energy was released in the formation of the new bonds than was required in the breaking of old bonds. So just realize that's called the activation energy, forming the activated complex. The products are lower in energy than the reactants, so we went from a higher energy state to a lower energy state. What happened to all that energy that was stored in the reactants? It was released in the form of heat, exothermic process. Okay, just to kind of drive the message
This
home,
is
let's
an
look at
energy
endothermic.
profile for nitrogen monoxide, NO, reacting with chlorine molecules, CO2, to produce nitrosyl chloride, NOCl, and chlorine atoms. Click on each of the regions, A, B, C, or D, as they appear to view the molecular changes that occur during each stage of this reaction.
Okay guys, so we're going to see we're starting with our reactants here, and then we're going to form the activated complex here, and then ultimately we're going to form the products here. So you can see, obviously, you can anticipate what's going to happen. There's going to be a bond that has to form between the chlorine, and it's going to combine with the nitrogen monoxide. So there has to be a breaking of these bonds and then a formation of those bonds. But in so doing, you're forming this high energy activated complex, which is responsible for the activation energy.
As the two molecules approach each other, an attractive force begins to form between the nitrogen of nitrogen monoxide and one of the chlorines of the chlorine molecules. This attraction is indicated by the dashed line. The bond between the chlorines begins to weaken, and the bond length increases.
So what they're saying is, as the bond is force of attraction is occurring between one of the chlorines and the nitrogen from the other molecule, the attractive force between these two chlorine atoms is weakening.
When molecules collide, they form an activated complex, a temporary species formed by the reactant molecules as a result of the collision before they form the product. In this reaction between NO and CO2, the activated complex is nitrile chloride, NoCl2. The activation energy, which is the minimum energy needed to initiate this reaction, is 85 kilojoules per mole.
So once again, guys, a very unstable activated complex is produced. In order to produce that, it requires 85 kilojoules of energy, but this is necessary in order to produce the products. It's an intermediate condition in the process of this reaction. But you'll notice this doesn't appear in the reaction. This is the reactants, those are the products, because it only lasts momentarily because it's so unstable.
At this point in the reaction, the bond between nitrogen and chlorine continues to strengthen, and the bond between the two chlorines continues to weaken.
And so you guys, just to kind of drive home, so if we didn't have 85 kilojoules per mole of energy, if it didn't have that much, right, we weren't at an appropriate temperature to have that much kinetic energy, so it would come up here, and there wouldn't be enough energy to form the activated complex, and so you would just remain, the reactants would just remain in their reactant state. But if we have enough energy, it's going to form the activated complex. It's really unstable, and so then what it'll do is it will proceed to a lower energy, more stable form, which will in this case be the products.
A bond is now formed between nitrogen and chlorine. The bond between the two chlorines has broken. The products of this reaction are nitrosyl chloride, NaCl, and chlorine atoms. The products are less stable than the reactants. The products have a higher potential energy. In this type of reaction, heat will be absorbed from the surroundings by the reacting mixture. The heat absorbed, or delta H, is 83 kilojoules per mole. This is an endothermic reaction.
So you guys see what's happening is there was more energy required to produce this activated complex than was released in the formation of the lower energy products. So overall, more energy was required than was given off. Overall, it is an endothermic process, right? Because the products are higher in energy than our initial reactants. And so how did that happen? It had to have absorbed heat energy from the surroundings. Okay, so this is just showing us, right, once again, this is called the activation energy. The difference between the enthalpy of the reactants and the enthalpy of the products is called the change in enthalpy, or the change in energy. And I think we've already looked at that. So the high point on the diagram, that's called the transition state, and it's forming, the compound that's formed there is called the activated complex. The energy gap between the reactants and the activated complex is the activation energy barrier. Once again, that's the minimum amount of energy in order for there to be a reaction. Okay, you guys look at this. You'll notice a different kind of a curve of the energy of the various molecules. So here's the kinetic energy on the bottom. Here is the fraction of the molecules. So for example, right when we take the temperature, you guys remember the temperature is the average kinetic energy of the molecule. So if I was getting the temperature of the room, which is at 23 degrees Celsius, once again, some molecules are moving fast, some are moving slow. So at a higher temperature, some molecules are moving slow, some are moving really fast. They have a lot of kinetic energy, but the vast majority are right here in the middle. And you guys will see, well, we'll just see a difference here. You'll notice when you have like a sample at a higher temperature, you notice the curve is more flat, right? And a sample of matter at a lower temperature, you still have a range of fast moving to slow moving, but it is a tighter, narrower range, okay? So at any temperature, there's a wide distribution of kinetic energies, which is what these curves are showing. But just realize at a higher temperature, the curve is broader and flatter than it would be at a lower temperature. As the temperature increases, the curve flattens and broadens, that's what we said, okay? And now what you're going to see is, thus at higher temperatures, a larger population of molecules has higher energy. Guys, let's say this line here marks an activation energy for a particular reaction. So you guys had a particular reaction. Just imagine if your sample is at a higher temperature, right, with a broader curve and a broader distribution, wouldn't you agree that a greater portion of those molecules at a higher temperature have the necessary minimum activation energy in order for there to be a reaction? Like, you guys just kind of look at the red curve right now. Wouldn't you agree that that's probably about 20% of the whole, of all the molecules? This would make up about 20%. So we'd say about 20% of the molecules have met the activation energy. We'll compare that with the same sample at a lower temperature. We still have a heat distribution, but now at a lower temperature, you guys see how the curve is smaller here. Wouldn't you guys agree this is probably at the blue curve? Wouldn't that represent only about 10%, if that, maybe 10% of all the molecules would have the necessary amount of energy in order to effectively react? So what that should tell us is that at higher temperatures, a greater portion of the molecules have the necessary activation energy, and therefore you're going to expect a faster reaction rate. Whereas at a lower temperature, less portion of those molecules have the necessary activation energy, and therefore less are going to effectively collide, and therefore that's going to result in a slower reaction rate. And that's essentially what this is saying. As a result, the reaction rate increases at a higher temperature. The sequence of events, okay, and this is kind of the main point of this lesson today, guys, is reaction mechanisms. And that's defined as the sequence of events that describes the actual process by which reactants become products is called the reaction mechanism. And a lot of times, you guys, we have to kind of speculate about this as a result, and speculate, but based upon experimental evidence. Because you think about it, in a reaction, what's the only things we see? We see the reactants, and then we see the products. We see what we start with, and then we see what we end with. But we don't get it. We don't see the steps that was taken to go from the reactant to the products. So reactions may occur all at once or through several discrete steps. Each of those steps is called an elementary process. So you can have multiple steps in a reaction. So here's kind of just a little summary. We could have a situation where it's unimolecular. As you might expect, uni means one. So you can have a situation where you just have a substance A and it's going to produce products. You know what would be a good example of this is radioactive decay. You have a radioactive element like radon. It's unstable, and so all you have is radon. It doesn't have to react with anything else, and it's just going to break down. It doesn't even have to collide with anything. When you write the rate law, that would be a rate law that's first order. Remember we talked about that last video lesson. Radioactive decay is first order. And what that means is, for example, right, if I doubled the amount of A, when you double the rate, when the rate at which it decreases, wouldn't it double? Because you have twice as much, you're going to have twice the rate of decay. Well, you can have, oftentimes what you have in chemical reactions are what we call bimolecular. As you might expect, that means there's two. So for example, you can have A, but in order for this to occur, there has to be a collision between two A molecules, for example, right? So two A molecules. And in that case, the rate law would be second order with respect to A. Because if you doubled A, if you doubled the amount of A, you would expect the rate to actually quadruple. Now I can kind of show that with ping pong balls, and if we doubled the amount of ping pong balls, you'd have actually quadruple the amount of collisions between those molecules. That would be second order. And then you can also have a bimolecular if it was two different substances, for example. And then as you might expect, termolecular would indicate that three separate species have to interact. Now you would imagine which one of these would be the most rare. I would think you would imagine it would be the termolecular, because you guys think of the chance that three different things are going to collide all simultaneously is highly unlikely. So usually when you have a situation where you have three different reactants involved in a reaction, typically that's going to indicate that there's more than one step, that it didn't just happen with three things occurring, because this situation is generally pretty rare. So in a multi-step process, one of the steps will be slower than all the others. Think about this, guys, right? You're looking at Plaza. Wait, you know what? And this is kind of showing in this case, Plaza A to go through, like, let's say a toll booth is really slow, and so there's a backup of cars here, but then it looks like when they go through Plaza B, they're just going through pretty quickly. But in this case, it looks like they're going through Plaza A toll booth relatively quickly, and then there's a kind of a slow up here at Plaza B. It could be the same thing in a reaction mechanism. Think about it, you guys. I think some of you guys have relatives in Mexico, and I think I go to Mexico relatively often. Now think about it. When you, let's say you have a relative right in TJ, right? And then let's say there's about 3 or 4 traffic lights from, let's say, Grandma's house to the border. So she lives in TJ, right? And so then you have to go through traffic lights. Let's say, each traffic light's like, maybe 30 seconds, 1 minute, right? But then, so you go do that, but then you come to the border, and then let's say, typical for me, a typical border wait, I don't have the Century Pass, is like an hour. Now let me ask you, if someone on the US side, let's say whatever, said, hey, why did it take you so long? Why did it take you so long to get back here to San Diego? How many of you guys are going to say, yeah, there was just a lot of traffic lights in TJ? No one ever says that. You guys were right, because it's not the traffic lights that ultimately determine how fast it took for you to get from TJ to San Diego. What are you guys going to mention? Oh, you're like, dang, yeah, the border wait was another hour, or it was an hour, right? So it's the border which is you might say, the rate determining factor. It determined really how fast you could go from TJ to San Diego. And in the same way, that's what we're going to be doing when we look at mechanisms, is which step is ultimately responsible for the speed of the reaction. So the overall reaction cannot occur faster than the slowest rate determining, I'm kind of running out of batteries here, the slowest rate determining step. So let's say we have a reaction here. NO2 reacts with carbon monoxide to form NO and CO2. Okay. Now, you could look at this as, maybe you would look at this as like a bimolecular one-step mechanism. You just think nitrogen dioxide, and that's kind of how we've looked at it up until now. Just kind of collides with carbon monoxide, and then it looks like, one of the oxygen atoms in nitrogen dioxide combined with the carbon monoxide form CO2, and now you have nitrogen monoxide. Okay, but experimentally, when you look at, you remember how you determine the rate laws, that's determined experimentally, right? You have to look at, at various concentrations, you look at the speed of the reaction, okay? Now you guys will notice, this is actually the rate law that was determined experimentally for this reaction. I'm asking what seems a little odd about that rate law. So look at the rate law and then look at the reaction. I'm hoping some of you guys would notice, you're like, wait a minute, I'm looking at that rate law, and you know what? The reaction obviously needs nitrogen dioxide and carbon monoxide in order to react. Yet I only see nitrogen dioxide in the equation. So that's what I was hoping you guys would realize, that you see carbon monoxide is not in the rate law. What does that tell you? The rate is not dependent upon the amount of carbon monoxide. Obviously, it needs carbon monoxide. Obviously, you're not going to have this reaction without it. These are the two reactants necessary. But the amount of carbon monoxide you have, or the concentration, has no bearing on the rate. What that tells you is that carbon monoxide must not take part in the rate determining step. You know, it's kind of like carbon monoxide, even though you had to go through traffic lights in TJ, right? So they are very much a part of your trip, but those had pretty much negligible effect on how long it took you to go from grandma's house in TJ to your house here in San Diego. So we would propose a mechanism. Carbon monoxide is necessary for this reaction to occur, but the rate of the reaction does not depend on its concentration. This suggests the reaction occurs in 2 steps. So this would kind of tell us that it's not, because if you guys think about it, if this was just a 1-step reaction in which these just collided, wouldn't you guys say it obviously would it would be affected by the amount of carbon monoxide? Because if I increase the amount of carbon monoxide, wouldn't you guys agree that's going to increase the amount of collisions between those, and that's going to increase the reaction rate? But the fact that it doesn't appear here would tell you, you know, this isn't a simple 1-step reaction mechanism. Okay, so here, okay, so they're showing you, like, okay, so they're likening it to the plaza here. So they're proposing this 2-step mechanism. First of all, I will say this: when you guys have to analyze if that mechanism is viable or not, let me see if I'm jumping the gun here. First of all, let's say this is a proposed mechanism. First of all, it has to make sense. Okay. So when you add these together, you better get your original equation. So look, you guys remember. So look, this is saying NO2 and NO2 collide together and form NO3 and then NO. And then look, the NO3 here is now used up here, so that we can cross out, because now they're saying the NO3 that was produced in the first step reacts with the carbon monoxide, producing NO2 and CO2. So then we look at what we have. We have NO2 and NO2 here. That's 2 NO2, okay? Plus, look, the CO, I'm just kind of adding down my reactants, produces NO2. But now look here, guys, I have 2 NO2 here, 1 NO2 here. So ultimately, when you guys agree, if there's 2 here and 1 here, it would just be a net amount of NO2 here. And so then what else have I produced? NO and CO2. And if you look, that is the original equation. So that's the first thing you want to do to see if this is a viable mechanism, right? We kind of propose what we think could probably happen. When you add up the elementary steps, you better get the regular reaction. So we see that is possible. So now in this case, what would make sense, and this is where we could propose this based upon the experimental evidence, and what was our experimental evidence led us to this rate law, that it is second order with respect to NO2. We find that whenever we double NO2, you guys see if it's second order, if you double it, when you square it, what does that happen to the 2? Doesn't it increase by a factor of 4? You're quadrupling the rate, and that's what they find experimentally. So we see NO3 intermediate is consumed in the second step, just like I said. And as CO and O, and then you guys see, we always get our rate law from the slowest step. Remember, the slow step is called the rate determining step. So we see as CO is not involved in the slow rate determining step, it does not appear in the rate law. So what you do is you take your slowest step, this is what determines the speed of the overall reaction, and then you write your rate law like that. So we see rate is equal to K. You guys remember it's always equal to the rate constant. And then we see, oh, I've got 2 NOs, so that means it is second order with respect to NO2. And you guys see that is our experimental rate law. So what we can say is this mechanism that's proposed definitely fits the experimental evidence that led us to this rate law. And we see that corresponds to the rate law that you would write based on the elemental step. So one last thing I want to note is realize the rate law, guys, is not written from your original equation. Notice it is not. It doesn't get, where does the rate law come from? It comes from the slow step in your reaction mechanism. So this is, the rate law is written from that, okay? But ultimately the rate law is determined experimentally. Okay, guys, the last thing we're talking about is catalysts. So catalysts increase the rate of a reaction by decreasing the activation energy. So just imagine we have these reactants and then it forms these products. Remember, you always have to form this activated complex, this unstable that requires energy to produce it, right? So this would be uncatalyzed. When you add a catalyst, you guys should know it lowers the activation energy. And you guys see, some people are probably wondering, what is this funky thing here? You know what it's showing? This is showing a two-step mechanism. So it's showing here, like, so it's first, here would be like the first elementary step. And then this would actually be the fast step because it doesn't require as much energy. And then this would be the second step. So this would be like a two-step mechanism, just like we had shown before, right? It's kind of like this. Even though this is a different reaction, you guys notice this was, oh, you know what? It's kind of the reverse. Here the first step was the slow one and the second step was the fast one. In this case, the first step is the fast one. You see why it's faster? Because it requires less activation energy. So you're going to have a lot more meet the activation energy to produce that activated complex. And then in the second step, you see it to form this activated complex, it's much higher. Therefore, that means that's the slower step. So this is showing a two-step mechanism with the first elementary step being the fast step, the slow one being this second step. So this ultimately would be the activation energy for this. The whole point, though, is just to see that regardless of how many steps there was, what did the addition of a catalyst do? It lowered the activation energy. And what's the result? If you have a lower activation energy, if the reactants need less energy in order to effectively react, you're going to have a lot more, are going to have that amount of energy, and that means it's going to be a faster reaction. That's what catalysts do. Catalysts change the mechanism by which the process occurs. So in this case, maybe it was a one-step process, where these molecules collided. And you know what? And that would make sense. Look, notice that there's three items here. If this was a one step, that would be termomolecular. That would mean all three had to collide all at the same time. The likelihood of that is not very much, and therefore, it's going to require, you're going to have a much slower reaction. But with the addition of a catalyst, it can maybe make it into, two collide and then it produces this activated complex, and then that activated complex reacts with the third one, and then ultimately produces it. Either way, less energy is required, faster reaction. So one way a catalyst can speed up reactions is by holding reactants together. Just imagine hydrogen reacts with this hydrocarbon, and so let's say this is a catalyst. Basically, it could bind the two substances together and then make it such that it's going to allow for the breaking of bonds to occur much easier. Here's a last term for you guys. There are enzymes. Enzymes, simply, guys, are biological catalysts. You guys, we have enzymes in our body which assist us in our digestion, which assist us in many different things. So, for example, you have a substrate. These are like biological terms. Let's say we have an enzyme. In fact, you guys, the vitamins you take act as coenzymes. So a lot of the bodily processes might happen without vitamins, but oftentimes they're going to be way too slow in order for there to be, optimum functional. So here's how an enzyme works. Once again, what's an enzyme? It's a catalyst. What does a catalyst do? It speeds up a reaction. How does it do it? By lowering the activation energy. Often what it does is it will help the reactants to orient in such a way so that when they do collide, because they do need energy, if they have the right proper orientation, they need less energy than they otherwise would need, and therefore you're going to have a greater portion of those molecules are going to have the necessary energy, and therefore it's going to be a faster reaction rate. So what will happen is the substrate or whatever's reacting will fit into the enzyme, and so what the enzyme will do will be assist in the breaking, let's say, of old bonds, and then the products form. That's going to happen much easier than if the enzyme wasn't present. All right, guys, that's all I got for you today. We'll see you guys next time.